In the video entitled Substitution Method and Exact Solutions Part 1, we discussed how to solve differential equations by way of substitution. This included types of differential equations of the form homogeneous and Bernoulli, as well as others in between. In this video, which is entitled the same thing but part 2, we will discuss how to solve exact differential equations as well as specific second order differential equations in which one of the variables x or y is missing. So we'll get started first of all working with exact differential equations. If you recently took a Calculus 3 course that is multivariable calculus, this should be familiar as we saw this when we were computing potential functions for conservative vector fields. So let's begin with theorem 1.6.1, a criterion for exactness. This is what we're going to be used to check to see if a differential equation is in fact exact. So we're going to suppose that we have functions m and n. You'll notice that those are just the functions before the dx and dy differential respectively. We will assume that they're continuous and have continuous first order partials on some rectangle that we're working on. If that's the case, then what we want to check, I'll highlight in orange, is that these partial derivatives are equal. Now I want to pull something to your attention here. Notice that the partial that we're taking on m is opposite of the differential that is attached to m in the dE. So m is attached to dx. We want to take its partial with respect to y. Same for n. We want to take its partial with respect to x. It is attached to the dy differential. So just keep that in mind. If you're able to conclude that these two partial derivatives are equal on your rectangle, then that implies that the differential equation is exact. In that case, that means that we have a particular method that we can follow in order to solve this exact equation. In particular, let's let f be the solution of this differential equation. So that means that if we take the partial of f with respect to x, we should get out m. And if we take the partial of f with respect to y, we should get out n. So we can set up these two equations that del f del x equals m and del f del y equals n. From those two differential equations, we can work backwards to recover f. So here is the method that we're going to be using while we're solving these exact equations. We're going to set up those two equations, which I have numbered 1 and 2, and pick one of those equations to work with. I will arbitrarily always work with equation 1, but you could just as well do this method working with equation 2 first. So what I'd like to do is take that equation and I'd like to undo the x partial derivative. So I'm going to do that by taking a partial integral, just following the fundamental theorem of calculus part 2, that if I integrate a derivative, those cancel each other out. So you can see that right here, we've integrated m with respect to x. Now remember here that m is a multivariable function. That's important. We're taking a partial integral of a multivariable function. So what that means is instead of tacking on a constant of integration in terms of plus c, we can no longer guarantee that that constant will in fact be a scalar constant. Since this is a partial derivative with respect to x, all expressions in terms of y are also considered constants. So to be extra careful, we're going to write that constant of integration as a function g of y. And we'll later determine whether that g of y is something in terms of y or if it is a constant after all. All right, so this is our first attempt at finding f. So here's our f function. But again, we would like to flesh out what g of y actually is. So what we'd like to do is go back up to the second equation, which we haven't used yet, to get more information about that g of y function. So we're going to differentiate f with respect to y and set it equal to the function n of xy. So now we're getting a new function and we're going to use it to solve for g of y. So solve for its derivative, g prime of y, and then integrate once more to find out a little bit more about g of y. From here, we're going to solve for the implicit solution. Notice that we're not even going to attempt to explicitly solve for y. And then typically we leave the constant of integration on one side and everything else on the other. I'm not real picky about how you write your solution. So if you don't write it in that exact form, that's fine. All right, so let's jump right into an example so that we can see this procedure in full. What we want to do first is we want to verify that this differential equation is exact, right? So that's part one, verify that it's exact. So let's check that first of all. All right, I'm going to start by taking the partial of m with respect to y. So remember, m is this first component function, n is the second component function. So that is, I want to take the partial with respect to y of x plus tangent inverse of y. Now we know that the x term will go to 0 because there are no y's in that first term. And then hopefully everybody remembers the derivative of tangent inverse. That's 1 over 1 plus y squared. All right, so there's our first partial. Next, let's take the partial of n with respect to x. So that's the partial with respect to x of, I'm going to break this up into two different pieces. This is x over 1 plus y squared plus y over 1 plus y squared. I think this makes it a little bit easier to see the derivative. This piece doesn't have any x terms, so we know that its partial goes to 0. And the first summand has a single linear x, which is going to derivate to 1. And so this leaves us with 1 over 1 plus y squared. And sure enough, those two partials do equal. And so that tells us that our differential equation is exact. From here, we'd like to move forward using that procedure listed above. So let's write out our two equations. I have the partial of f with respect to x is m, or x plus tangent inverse. And I have the partial of f with respect to y is x plus y over 1 plus y squared. And then from here, I would like to do my first attempt at recovering f. And like I said, I'm going to just work with that first equation, but you can do it either way. I want to take the partial integral with respect to x of x plus tangent inverse of y. All right, so let's integrate both terms here. This is a 1/2 x squared plus x tangent inverse of y. And then here again, instead of writing a plus c, because this was a partial integral of a multivariable function in x and y, it could be a constant or it could be some expression in y. So we're going to just write it generically as g of y. Now here again, this is our first attempt at coming up with f of xy. So now we'd like to use this second equation. We have not used that piece of information yet. And you'll notice that it's the partial of f with respect to y. So for step 2, I want to take the equation that I just found, which I'm highlighting here in green, and I'm going to take its partial with respect to y. So the first term goes to 0. The x lives on. The derivative of tangent inverse is 1 over 1 plus y squared. I don't know what g of y is, but I'm taking its derivative with respect to y, so I'm going to use the prime notation. This prime notation is clear in this sense because that's a single variable function, so there's only one variable to take its derivative with respect to. And now what I'm going to do is I'm going to equate this to what's highlighted in orange, which is also the partial derivative of f with respect to y. Now here again, I think I'll go ahead and split this up as x over to the denominator plus y over the denominator. And what I see here is two terms that are equal. I'll cancel those out on both sides of the equation. And now I can equate what's left over. So I have g prime of y equals y over 1 plus y squared. All right. So next, we're going to do step 3. We'd like to solve for g of y. G of y is just going to be the integral of y over 1 plus y squared. This is no longer a partial integral. This is a standard integral because we're working with a single variable function. Let's go ahead and set up a u substitution here for the denominator. So du is 2y dy. So this gives us a 1/2 integral of 1 over u du, which gives us a 1/2 natural log of u plus c, or that's an honest to goodness scalar constant of integration. And then resubstituting for u, I have 1 plus y squared. Now, technically speaking, we know that 1 plus y squared is going to be a positive number, so you could drop the absolute values if you wanted. Finally, we're going to take this value for g of y, and we're going to substitute it up above here in that green equation. So we have f of x y equals 1/2 x squared plus x tangent inverse of y plus 1/2 natural log of 1 plus y squared plus c. Now, I would absolutely accept this for full credit. As I mentioned, the book tends to write the function on one side and the constant of integration on another. So they tend to write it as 1/2 x squared plus x tangent inverse of y plus 1/2 y, 1/2 natural log of 1 plus y squared equals c. And furthermore, they're likely going to get rid of that 1/2 fraction out front. So if you were to take this entire differential equation and multiply by 2, they would write their answer as x squared plus 2x tangent inverse of y plus the natural log of 1 plus y squared. And then instead of writing this as 2c, this is something common in differential equations called absorption. Instead of writing the constant as 2c, whatever c was to begin with, 2c is itself just another constant. And so we just absorb that 2 into the c and leave it as c. So I believe this is how the book is writing their final answer. But like I said, I'm not too concerned about the format in which you write your final answer as long as it's correct. All right, so that's an example of exact equations. We end this section talking about how to find solutions of a very particular type of second order differential equation. So first I have a remark here. A second order DE involves the second derivative of y of x and has a general form of, notice that it's involving x, y, and possibly its first and second derivative. Now it may or may not include y and y prime. What's important is that it must include y double prime in order for it to be classified as a second order DE. Now, what we're going to concern ourselves with are second order DEs in which one of the variables, either x or y, is missing. And so let's take a look at how we're going to do that. I have 2 bullet points here. The first one is if y is missing. So we have x, potentially y prime, and definitely y double prime. So if that's the case and y is missing, how are we going to move forward? Well, we're actually going to use a substitution just like we were in part 1 of this section. And our substitution is going to be letting p equal y prime. Now you'll notice that I also wrote that in Leibniz notation, dy dx, and you'll see why here in a moment. Our goal is to write this entire DE in terms of x and p, because remember, y is missing. And so if we want to express y double prime in terms of y and or in terms of p and x, well, that's just going to be the derivative of p. So we'll write that as dp dx. Now what we're going to do is we're going to transform this differential equation by plugging in these values for y prime and y double prime, and we obtain a new differential equation that's strictly in terms of x, p, and p prime. This has reduced it from a second order differential equation to a first order differential equation. And these problems are all written so that you should be able to solve it from previous methods. So check if it's homogeneous, check if it's Bernoulli, check if it's linear or separable, and then move forward with whichever method is appropriate. All right, the second bullet point is if X is missing. And we're going to follow a similar procedure. However, this one just has slight additional complication to it. Now, what you'll notice is our substitution is going to begin exactly the same. Because X is missing in this differential equation, we would like to write this fully in terms of Y and P. So right out of the gates, we have an issue here. Look at how we've written P. It is in terms of dy dx, and we want to get rid of X terms. That includes the dx differential, which we're seeing in the denominator. So this is where things get a little bit hairy. So now let's take a look at y prime. As it was in the previous bullet point, its derivative is dp dx. However, we do not want dx. So what we're going to do is we're going to run through the chain rule, and we're going to say, well, p was a function of y. So the chain rule says I can take the derivative of p with respect to y and multiply by the derivative of y with respect to x. Again, we love Leibniz notation because you can essentially see the cancellation here, that those y's go away and you get that x back out. But we want those y's. So instead, now we're going to say, okay, well, what was dy dx? I'll highlight it up here. Dy dx was p. So we're going to replace that dy dx with a p, and we'll leave dp dy. So again, the major difference is in bullet point 1, y double prime is dp dx. In the second bullet point, y double prime is p dp dy. They're actually equivalent. It's just that in one of these methods, we want to write everything in terms of p and x. And in the other method, we want everything in terms of p and y. So now plug all of these values in. You should have a differential equation in y and p. And then again, check to see which familiar differential equation this is and solve appropriately. So I have problem 54 from the textbook here to work out. We have y double prime equals 3 y prime quantity squared. So the first thing we want to do is identify which variable is missing. And here we know that the x variable is missing. In this case, our goal is to rewrite this as a first order DE in terms of x and p, y and p. So we want to write this in terms of y and p. And so let's go ahead and set up our p variable. Let p be y prime, which is dy dx. Okay, and so if I take the second derivative, y double prime, that is just p prime, where here it's understood that all prime notation is with respect to x. But remember, x is missing. We want to get rid of the x's. So let's write this by way of the chain rule as dp dy times dy dx, but dy dx is p. So I run through this every single time just so that I'm not having to memorize things. I just remember the chain rule. Now what we're going to do is we're going to replace everything in the differential equation with what we've just stated. Y itself is fine, so we'll leave that. We don't want y double prime, so that is p dp dy. And on the right-hand side, we have 3 times p squared. So you'll notice that we've now reduced this to a first order differential equation where p prime or dp dy is the only derivative involved. This is a separable differential equation. So I'm going to move all the p's to the left and all the y's to the right. So that's going to leave us with a 1/3 times 1 over p dp. And that equals a 1 over y dy. All right, so let's go ahead and integrate. This is 1/3 natural log of the absolute value of p equals the natural log of the absolute value of y plus some constant of integration. Now I'm going to write that as C1 because we're going to end up having multiple constants of integration. One thing that you'll notice here is that way up top, they say assume that x, y, and y prime are positive. This is just so that you can omit those absolute values in your natural log. And so that's going to simplify things a bit. Let's go ahead and drop those. I'm also going to move the 1/3 over. So I'm going to write this as the natural log of p equals 3 natural log of y plus c1. Here again, I'm not distributing the 3 to the c because I'm absorbing it. 3 times a constant is still a constant, so you can just leave it as c. And then finally, I'd like to solve explicitly for p. So I'm going to apply the natural exponential function here. P equals e to the 3 natural log of y plus c1. It is common here to break up those exponentials, okay, using exponential rules that if you have addition within the exponent, it drops down as multiplication. But again, this is itself just some other constant. I'm going to use logarithm rules to pull that 3 up front, or I should say in back of the natural log. So it becomes a natural log 3y cubed. And then we see simplification here with our exponential and natural log. So this whole thing reduces to c1 y cubed. Okay, so this is where we're at for p. Now remember what p was equal to. Way up top here, that is dy dx. So I currently have p equals c1 y cubed. I'm going to replace p with dy dx. And now we're back in terms of x and y, but we have a single order or first order differential equation. And now we're going to run through this process once more. We're going to separate variables. I have a y to the -3rd dy equals the integral of c1 dx, and then I'll integrate. So this becomes a -1/2 y to the -2. I'm going to write my plus c on the other side. This equals c1x plus some constant c2. And then we'll go ahead and simplify a little bit. Let's write this as, I'm going to multiply both sides of my dE by -2y squared. So that gives me 1 equals -2y squared times this linear expression, c1x plus c2. And quite frankly, I would accept this for full credit. However, I'm going to continue on in red so that you can see how the back of the book writes its answer, which is not my favorite. But again, I would like to be very clear so that you're not confused when you're looking in the back of the book. The book does, in my opinion, some unnecessary simplification. So they're going to distribute the -2 inside the parentheses. Write this as -2c1x minus 2c2. Actually, we could have omitted that step. So I'm now going to actually factor out a -2c1. So I have a -2c1y squared. And then what does this leave us with? We have our single x, but we pulled out a c1. So we have division by c1. And so the book does this kind of silly substitution. They say, let A equal a -2c1 and let B equal c2 over c1. So they write their final answer as 1 equals ay squared times x plus b. Now, admittedly, this answer does look a little bit cleaner, and a and b are just constants. So it's fine to do this. But like I said, I feel like this is extra work. So there's no need for you to write your answer in this way on quizzes and exams. But I wanted to run through it just so that you have an understanding of how the book is writing their answers. All right, so this concludes section 1.6. This is kind of a long-winded section. So when you're working through this homework, make sure you allocate a decent amount of time to get through it. It is a long section. And so we will continue on with chapter 2 in the upcoming videos.